Okay, hello everyone. Thank you for coming to this presentation on hunting blockchain clients bugs with Concolic execution. I'm Karolina. I'm doing a PhD between Telecom Paris and Ledger Dungeon. The Ledger Dungeon is the security research team at Ledger, and we are working on this topic since 2 years now. Before we start, I wanted to ask you a question. Can you recognize this guy? Yeah, just say it. Who is it? Gopher, okay, right, Gopher. So that's this little animal representing the Go language, Go community that was designed by Google in 2009. And Go language, as you know, probably is used a lot in our ecosystem. So here's just a representation of how we can evaluate the impact, or at least how much Go is securing our ecosystem. So we can estimate that it's at least $60 billion that can be that rely on Go security through Ethereum ecosystem, layer 2s, multi-chains. So that's a lot, and that's why when I started my research, I wondered how much Go is secure, because it's not such old language. So I tried to look at that. And while doing that, I was also looking to the vulnerabilities that exist and that have been reported to the blockchain clients mainly, because Go is mainly used in blockchain infrastructure, also in backends and other types of infrastructure. And for blockchain clients, you can see vulnerabilities that have been reported to the CV database, but as you know, it's kind of old and not really relevant. So we explored also audit reports for all the main providers, and we looked to the existing bugs and how we can improve the code security and reduce the number of them. And looking to the Go tool chain and to the existing tools for Go, we saw that there was a lot of good static analyzers, fuzzers, also carry-based tools, which are good. Of course, they are part of the ecosystem for several years for most of them. But what was surprising is that we didn't have any specialized symbolic execution tool. And just for those who are not familiar with symbolic execution, it's just one of the techniques that enable you to analyze the security of a code. So normally you start with static analysis, which is just scanning for bugs. You then normally do fuzzing, just sending concrete values to your code and trying to make it crash. You heard a lot about formal verification, which is a good method to mathematically prove the correctness and convergence of your code. And in the between of fuzzing and formal verification, we have hybrid methods, somehow based in symbolic execution. So this consists of just taking your code and trying to look at all the execution path of it and look to the one where there is a vulnerability at the end. So that's what we do. And to be even more precise, there are different types of symbolic-based execution tools or methods. So here I wanted to, for the ones that are the most experienced among you, just to give you the difference between what we call compositional execution and concolic execution. So we saw symbolic execution. Concrete execution is just when you normally execute your code with concrete values, and you can combine these two because sometimes symbolic execution explodes. So when you have too much path to analyze, at one point it just crashes. So you have to somehow mock or add concrete values at some path of the at some places of the execution to keep the explosion. And we can do it with compositional execution. That's why I think runtime verification is doing with their tool Symbolic that is focused on application layer. And in this work, we choose to do concolic execution, which is both concrete and symbolic, because we think that it gives the most tools and the most material to have a good analysis of a program. So that's just what it is. And then we had to look at the existing tools in the Web2 ecosystem, because If you remember right now, we are looking to Go. Go is mainly used for infrastructure, as I told you, for Go clients, Go Ethereum, all the forks, the layer 2 forks that are based on Go. It also happened that several smart contracts are also written in Go. But for Go, we wanted to know if existing Web2 tools can handle Go binaries. And for that, we had to look at the method they use, the intermediate representation they use. So this is a concept that is just taking an intermediate level between the language that's the source code of the binary and using this representation to be able to better analyze the code. So this is the intermediate representation. And also you have a SMT solver. Most of the time it's Z3, but there are also others that are specialized for special purposes of finding special types of bugs or verifying properties. So this is all the thing you have to look for. For Go, what was striking is that you can't really analyze a Go code statically because the runtime and the garbage collector are heavy and they are deeply linked to the code. So we tried to, for instance, take a blockchain client and to compile it as just a library, but that didn't work and that was not even realistic. And that's why we had to have a tool that was able to handle the runtime and the garbage collector, which means handle syscalls and CPU instructions. So knowing that, you have to go low level, and most of this tool didn't have the symbolic implementation of syscall instruction or CPU instructions. That's why we wanted to propose a new tool, which is called Zoria. It's written in Rust. It has the intermediate representation that is the P code. It uses Z3, and it is able to handle most of the runtime, the Go runtime, and the garbage collector. And yeah, let's deep dive into these choices that we have made. First, the intermediate representation. We could have chosen others because for instance, LLVM is used a lot, but it happens that the Go LLVM compiler is not maintained anymore by the developers, so we couldn't really use it. Others, specialized languages, have less support than Pcode has, in our opinion. So Pcode is associated to the Ghidra disassembly tool. For those who do reverse engineering, this is one of the only open source free tool that is well used and maintained, especially by the community. And it also uses an intermediate representation. So using it for our Concolic execution method sound a good idea, especially that it's quite granular, which means that you really go down in terms of the stack. So you will ask me, what does the P code look like? This is a screenshot from Ghidra interface. You see the addresses of the program that you analyze. In the middle, you see the Intel set instructions. So here we have move and CMP exchange. Okay, whatever. What I just wanted to show here is that for one instruction like CMP exchange, which is one Intel instruction from the Intel set, you have many P-code instructions. And that shows somehow the granularity of when you are looking for vulnerabilities and patterns of vulnerabilities, that you can somehow understand that we can go in a precise analysis of the path that can lead to a vulnerability. Yes, so this is our intermediate representation. And since I told you that we have chosen to do concolic execution, we have to implement each of these instructions both concretely and symbolically in Rust with the Z3 crate. So yeah, so each time there is an operation that is done, we do it both concretely and symbolically. And you can also see here registers and memory spaces. So we also have implemented that CPU registers and memory section symbolically and concretely to do all this operation in the both way. And this is the overview of our contribution, of our contributions. So when you take a target binary, in our case it is mainly Go binaries in ELF format. We generate their picot, so it's a file, and we use for that picot generator, which is a homemade also tool, because there was not easy way of extracting the picot from Ghidra, so we had to go through things to do that. We also implemented a parser. And since I told you that we do concolic execution, we also have to dump the CPU register values and the memory regions to know what are the values at the starting address that we have chosen. So we can start the execution from start, from main, from any address of a function, and do that because of this mechanism. And then the execution goes through Zoria. I hope you like the logo. It's a cute owl. I hope it's okay. And yeah, and at the end you have in the execution logs statement if Z3 has found any satisfiable states or not, given the invariant that we have chosen. So here is just the first strategy. It's very, very simple. It's a small piece of Go code where you see that there is a nil map, and you try to get a value from the nil map, but that triggers a panic because it's a nil map. This is a very simple code, and you expect that a symbolic execution tool would find this. However, so yeah, that's just the workflow. You choose, for instance, the starting address, which is start, and your binary, and you want just to find this because it's straightforward. But it happens that the state-of-the-art tools like Radius2 or Miasm are not able to find this. The reason is very simple, is that these tools have been built for C or C++. So when these tools look for these vulnerabilities, they look for instance, actually a pointer to be, a null pointer to be dereference. However, in Go, that never happens because the compiler is smart, so it will not let the execution to dereference a pointer. So it will lead the execution to a function that's called null pointer nil panic. So that's what we are looking for in Zoria. And that's why we just can find this. But this is a very simple example. Also wanted to underline this important point, which is P-code is used in Ghidra. And with Ghidra, you can analyze many types of binaries, including C, C++, Rust, all other types of languages. So since we are working with P-code, Zoria is also in theory able to do concolic execution for any types of binaries that can be translated to P-code. So we also wanted to try if Zoria is able to find these three simple vulnerabilities in C binaries. And yes, it was able. So yeah, that's the conclusion. But just what it requires is that it requires us to write the right invariant at the right level. So for C binaries, for instance, you look at the store instruction if there is a null dereference that is being done, and so on and so on. So you have to do it manually, but once it's done, it can be detected for any binaries and any function. So that's kind of can help. That's the ongoing work, strategy 2 and 3, which consists of starting for the strategy 2, starting at main. So for Go binaries, main is main.main, okay? And we want, the strategy is that the tool is designed for developers who build, for instance, layer 2s, who have FortGet, and who want to check if the implementation is good. So they know values that make succeed their binaries. So for instance, here we work with a broken calculator, which has this condition. It does any type of calculation, plus, minus, divided, etc. But if the two operands are 5 and 5, then it does a nil panic. That's just a test binary that I have been using for the development of Zoria. And the goal here was to know if Zoria would be able to say to me that if input 1, input 2 equals 5, then there can be a panic, even if I give to it 2 plus 3. And this is a kind of simple example, but technically it requires some engineering. For instance, you have to follow the arguments of the binary which are stored in os.args, and then each time that there is a conditional branching, you have to explore the non-taken path to see if possibly that could lead to a panic. So that's what we do, what we call the negated path symbolic execution, which here enable us to find this type of vulnerabilities. And the strategy tree is the same, but then you start at a function. So here is just a function that parses a string. And in terms of background and engineering, you have to get the function signature to be able to know where are stored the arguments of the function, what are the types, and then to generate the correct symbolic variable that correspond to the type. So, for instance, here we know that the two arguments. We have a function that parses a string, and the string has a pointer and a length, and both will be stored in a register RCX, RDX, and so we have to follow it symbolically and concretely during all the execution of this function. So yeah, that's just two examples to show what we do and how it's a bit done in the backend. So our challenges are also to implement the symbolic length of argument of a binary and a function. In short, we just want to be able to see if there are overflows or underflows, and this concept is very interesting for that. Work on a Concolic multi-threaded execution with a symbolic Go scheduler, because for now we can only analyze mono-threaded binaries. There are all these tools that I showed you before, they all work for mono-threaded binaries, ours too. But the goal is to analyze real-world binaries. We have to handle multi-threaded symbolic execution. So that's the next step, and it's a big step. And also write relevant invariants. For now, the only invariant that we have is that the execution can never go into a panic function. That's the main argument. It's generic enough, but we still have to think about other relevant invariants and maybe also more blockchain-oriented. To answer your question, also we can write invariants in source code, in like macros, and compile the binaries with them and see if the execution can also follow, validate or not these invariants, just in parentheses. And how far are we from real-world scenario? We are currently trying to automatically reproduce bugs that have been found in manual audits. Hopefully we will share some results soon. And of course this symbolic Go scheduler that we are thinking about that for several months, and hopefully also we will suggest something in the next months. Yeah, so that's the conclusion. Zoria is the first Concolic execution tool using Ghidra P-code as intermediate representation and optimized for analyzing Go binaries. We have open sourced Zoria 1 month ago, so that's why I'm doing this talk here. Even if everything is not finished yet, I really look forward for your feedbacks. If you can test it, if you can report issues, if you can do anything that can improve this. It has been peer reviewed also and accepted in academic conferences, so it's already in archive. You can also look for the paper. And yes, I think I'm done. Thank you very much.
Yeah, so we have time for a couple questions if anybody has a question.
Thank you for the talk. Very cool. Also very cool tool. I'm still trying to understand what is Z3 and what do you use it for.
Z3 is a SMT solver. So it's we use it if I go here in the graph here. So it's a satisfactory module theory solver. So when we write an invariant, for instance, that the execution can never go into a panic function, we then, if we are in a path of the execution, when we detect a panic, we ask Z3 what were the conditions that can lead to this path, which mean in our case we ask for the arguments of the function or of the binary. So if we are here in this case that we panic, we at this point we ask Z3 what are the values of RCX and RDX, which were the arguments of the function that could lead to this panic, and same for the case when we start at main, and that's how we then can find that it's 5 and 5 because of all the symbolic constraints that we have accumulated until this conditional branching. And if you want to know more in the GitHub, I have some examples of how it looks like in the technical side.
Okay, thank you. And also another question. Why does it work on TinyGo and not with the native Go compiler?
Yes, so TinyGo is the Go compiler that was designed for tiny spaces like microprocessors, and it generates a binary that is monothreaded, so one thread. And for now, as you see, our analysis goes from a starting address to the next address to the next one, but we are not still able to create a new thread. So that's the only reason. If I would give a binary compile with a classical Go compiler, Zoria would get lost, but not only Zoria, all other symbolic execution tools, because they are not done for that yet. So it requires some optimization, because if you just duplicate the state each time you have a new thread, again, you have an explosion. So you have to do optimization to, for instance, only duplicate the register or the memory that is relevant and so on. So yeah, for now, this is where we are.
Awesome. That's all the time we have right now.
Thank you very much.
Cool.